So, in the previous videos, we have seen examples to ensure that the system is inherently safe, whether by proper design conditions or by considering fail-safe position. However, in many cases, we cannot achieve the design pressure or temperature that shall protect us from the upset. For example, when we talked about recycling the gas from the compressor discharge to the compressor suction while the recycle or surge cooler is down, this shall cause the compressor to compress the hot gas and the temperature shall increase drastically. This shall even cause more severe issues in reciprocating compressors. Here, we cannot consider a design temperature that guarantees this situation. That's why we should find another way to face this scenario. Here, we shall go to the next step, or in other words, the second layer of protection, which is to prevent the high temperatures by preventing the source of risk itself. So here, when the temperature transmitter needs a very high temperature, the shutdown system shall send a high temperature alarm, in addition to a signal to the compressor's motor in order to trip the compressor. Here, the source of hazard, which is the compressor running, shall be prevented from increasing the gas temperature by stopping the source. So the compressor is no more running, hence the temperature cannot be increased anymore. This can be applied to many examples. So, when the level of the vessel reaches a very low value, we shall need to protect the pump from cavitation. So here, the level transmitter shall send a signal to the shutdown system, which shall trip the pump motor while sending a low level alarm. Or if we are having a positive displacement pump, which doesn't have a shutoff pressure, unlike the centrifugal pump. So in case some blockage occurred in a positive displacement pump, for example, if this valve was closed, we shall need to trip the pump at a high pressure signal. So in most cases, we don't need to add a protection at centrifugal pump discharge, as we can just consider the design pressure of the pump shutoff pressure, as we have explained in a previous video, and this makes the system inherently safe. But in case of a positive displacement pump, this cannot be done. In this case, we shall need to stop the pump itself. Another example can be shown in a reactor which is heated by steam. We are afraid of overheating due to excess steam. So we shall add a shutdown valve on the steam inlet to stop the steam flow and protect the reactor from overheating. So in these scenarios, we are afraid of some accidents or upsets and the system is not inherently safe. So we are adding logic to stop the system when such scenarios can lead to an accident.